Welcome to part 2 of the TackleBox hook management walkthrough. In this video we will go over forward pre-hooks and backward hooks, and introduce methods for filtering calls to activate or deactivate module hooks. In this walkthrough we will be running the XLM transformer, imported from Hugging Face transformers, on the multi-30K machine translation dataset, imported from TorchText. We will be using tokenization with spaCy. Please consult the requirements.txt file for a full list of notebook dependencies. After setting up the dataset and loading the XLM model, we load a single batch of source and target data and define our loss function. We'll initialize the hook manager, then create a dictionary of modules to register our hook functions on, including the word embedding and final attention layer of the transformer. We've defined two hook functions below. Our forward pre-hook, 0 input, is passed a module and its inputs and sets the value of all input tensors of data type float to 0, then prints out how many of these inputs had a float data type. Our forward hook print mean simply prints the average of the first input and first output in the tuples. Let's register both hooks across all modules and named modules, deferring activation by setting activate equals false. We saw last time how context methods can be combined with torch.nograd to create more organized code. Let's try that now with hook_all_context to activate all our hooks and see what they're doing. We first see that the embedding's input was not set to 0. This makes sense since the input to the embedding is a long tensor of word indices and would therefore not be zeroed out by our hook. One of the final attention layer's 2 inputs was also set to 0. This also makes sense since the input to the attention layer consists of a float tensor of outputs from the last layer and a Boolean tensor representing self-attention masks. This is reflected by the 0-valued means of the final attention layer printed by our printMeans hook. We can pass the category kwarg to filter which hooks will be activated by hook_all_context. Let's try setting it to forward hook and see what happens. Notice that our forward pre-hook, 0 input, is no longer being called, and the final attention means are no longer 0. This is because the category argument is restricting hook activation to forward hooks exclusively, so 0 input is no longer being activated. Another option is to pass the hook types kwarg an exhaustive list of all functions that we wish to activate. Let's try passing hook types a list containing print mean. Notice that this has the same effect of limiting hook activation to print mean. Let's dig into backward hooks now. Backward hooks are passed a module, a tuple of gradients with respect to inputs grad in, and a tuple of gradients with respect to outputs grad out. If an element of the input or output tuples don't require gradient, then the corresponding element of grad in or grad out will be none. We've defined a simple backward hook, print grad shape, that prints the shapes of the first input grad and output grad elements in the past tuples. Let's register print grad shape to the final attention layer. Since this module was previously registered with the hook manager, we don't have to specify a module ID, and can pass it as an arg rather than a kwarg indexed by ID. Once registered, we'll activate only print grad shape using hook_all_context with the category kwarg set to backward hook. we see that our backward hook is executing successfully. When registering backward hooks with TackleBox, you have the option of registering hooks that require input and output data from the forward pass as well as their gradients. An example backward hook, print outputs with grad, is given below. The function receives grad in, grad out, inputs, and outputs, and prints the data of each element in output along with the class of the corresponding element in grad out. We'll register this hook on the final attention layer, as we did with print grad shape. This time, we'll also pass retain forward cache equals true to communicate to the hook manager that its call signature requires inputs and outputs, as well as gradients. We use the hook types quark again to activate only print outputs with grad, and again see that the Boolean self-attention masks have null gradient at the corresponding positions in grad in, thus demonstrating the correspondence between elements of the outputs tuple and those of grad out. The final core functionality of TackleBox is hook removal. There are three main methods that are used to remove hooks permanently so that further hook activation calls will no longer affect them. Let's list out the set of hooks that we've accumulated thus far, then use these methods to thin them out. The function removeHookName lets you remove a specific hook function from a specific module. Other registrations of that same hook function will remain unaffected. We can use this approach to unregister printMean from the final attention layer. RemoveHookFunction will unregister a hook function entirely, removing all registrations of that hook across all modules. Let's use this approach to unregister zero input from both the embedding and final attention layer. Finally, removeModuleByName allows removal of a module entirely, unregistering all hooks from that module. We'll remove all hooks from our final attention layer so that we're left with only our printMean hook registered to the word embedding. This concludes the walkthrough of hook management using TackleBox. I hope this tutorial helped illuminate what TackleBox has to offer. Thank you for your time, and happy experimenting.